Good morning to everybody. Welcome to the mass transfer course. Today will be lecture 15. We have started our interface mass transfer, and in last lecture we have seen that in separation processes generally two phases are in direct contact and solute will diffuse from one phase to another phase, and in this process there are three steps. First step is diffusion of solute A from bulk to interface in G phase or gas phase. Then there is at the interface there is a conversion of interfacial concentration AI to XAI, that is the step 2, and third step is diffusion of XAI solute from liquid L phase of interface to bulk. So there are three steps, and in the interface there is equilibrium will exist, because interface the resistance is almost zero. That's why there is always equilibrium will exist. And we have discussed about the equilibrium curve of two phases. How can we make this equilibrium curve? And then we took some overview of thermodynamics in equilibrium. We discussed about the Raoult's law, Henry law, and also for liquid system we discuss about the partition coefficients or distribution coefficient. Today we will discuss more about this interface mass transfer. So this is our interface. This is the Z equal to 0, and this is your gas film. This is my liquid film, and this is bulk gas. This is bulk liquid. So YAB, and this is YAI. Then YAI will convert to XAI. Then this. So if I take the flux at the G phase or gas phase, then Na will be KY into YAB minus YAI, because this is the concentration at the interface. So I can write this one. This is the flux, and if I take this same thing in terms of liquid side, Na equal to Kx, then it will be XAI minus XA, isn't it? So to calculate the flux I need the KY. Now we can calculate the mass transfer coefficient KY, that already we have learned. YAB, it is the concentration at the bulk phase. Okay, generally we can measure this and it will be known to us. And YAI is the concentration at the interface for the gas phase. Okay. But this is very difficult to determine what will be the Y. So if I can calculate the YAI, then if it is known, then I can calculate the flux. Similarly, for liquid side, if you take the from liquid side point of view, XAB, the bulk concentration at the liquid side, it will be generally known, or we can measure. See, bulk phase concentration can be measured easily. Okay. So generally YAB and XAB it will be known. Again here I can calculate the Kx, what is the mass transfer coefficient from the chapter 3 knowledge, I can do it. And here also what is the XAI, it is known. Now if I can calculate XAI, then I can calculate the flux. Okay. So to calculate the flux in interphase mass transfer, what are the interfacial concentrations are to be known, either YAI or X. But you understand that it is very difficult to determine. You cannot measure this one in a process, in a steady state process. What is the interfacial contact is very difficult, but somehow there is a way. Let's see how will we calculate the interfacial, or either YAI or XAI. So if I can calculate this either this or this, then I can calculate the flux for the system. And in this case, definitely this Na, whatever the flux from the gas phase side, will be same as this Na, because how many moles will transfer from gas phase to liquid, same will come here. So what are the flux moles per unit area second, okay, moles per kilomole per meter square second, that will be same. Now how will you determine the interfacial concentration? And what I know that at the interface the YI and XI are in a equilibrium. That knowledge we have. So I can write, so this is my coordinate and this is my equilibrium curve, YI equal to phi XI. So this equilibrium curve for a particular system, how will we generate that? All now I know from the last day discussion. Okay, now this point, this is the point XAB and YAB. Okay, so let's take we have taken the case of absorption of carbon dioxide from the mixture of carbon dioxide, hydrogen, nitrogen through ethanol. So that YAB, that concentration will be this, and XAB will be low. Okay, so what is the bulk concentration of gas phase and what is the bulk concentration at the liquid phase, that is known to me. So this M point is known to me. Okay, because I told that this what are the bulk concentration, that is generally it can be measured, and I have this equilibrium curve for this system, and generally for a particular system you can develop this equilibrium. But I don't know that what is the interfacial concentration, YAI, XI. Okay, so Na I can write KY into YAB minus YAI, okay, equal to Kx is equal to XAI minus XA. That I can write, because flux, whatever will be, whether I calculate this flux based on gas phase or it can calculate based on liquid phase, but it will be same. Now here I can write YA. Now if I take this one, YAB minus YAI, okay, this is, if I take this negative, XAB minus XAI, negative sign, so minus Kx by Ky. So YAB minus YAI, XAB XAI, this is minus Kx by Ky. This is the slope, and this is the mass transfer coefficient for liquid phase, and this is for mass transfer coefficient in gas phase. So this is the slope. Now if I take this one, okay, from this point is known and I know this slope minus Kx Ky, then if I take this slope and go straight, and when I will touch this point in the equilibrium, that is end point, and that will be my YAI and that will be my XI, isn't it? So to get the interfacial concentration, because interfacial concentration I know it is in equilibrium, so for that you need the mass transfer coefficient for both gas side, liquid side and gas side. and if you see this, what is the slope? This is YAB minus YI, YB minus YI, and YAB YI. Okay, then XAB XAI. Okay, then that negative XAB XAI, and the slope is coming. So now I can determine in this way you can determine the interfacial concentration. But how can we? It is possible because interface is at equilibrium. That's why I take this point. This point is known. I will take the slope of minus ky kx ky, and I will go straight, and where I will touch this equilibrium curve, and this will be my interfacial. This is for yi, and this will be my x. Now from the YAB minus YAI, this will be gas side driving force. Okay. Similarly, XAI minus XAB, this will be my liquid side driving force, isn't it? So here we have learned that how to determine the interfacial concentration. Now this is one way, but generally YAB and XAB is known. So can you make something driving force as a YAB minus XAB in a equal to some coefficient, that is called, let's take overall mass transfer coefficient K. So why overall I am telling? Because I am taking the driving force that bulk concentration of gas phase and bulk concentration of the liquid phase. Because generally to calculate the interfacial concentration you have to do the previous exercise, but YAB and XAB will be known to me. So if I take this as a driving force, and then it will be similar and corresponding that mass transfer coefficient, that overall mass transfer. Why? Because here I am considering within this mass transfer coefficient I am considering both gas phase and liquid phase. But here one problem is, it is YAB, this is for gas side, this is for XAB is liquid side. So here people what do, XAB is there, they go to this equilibrium curve, okay, and corresponding the YAB star. So what is YAB star? So this is the equilibrium concentration of XAB. Okay, because you know YAB and XAB minus you cannot do, but you have to convert in a single phase like this. So instead of doing this, I can easily make YAB minus YAB star, where YAB star is the equilibrium concentration of the XAB. Okay. So this driving force here, if you see, no problem, this is based on the gas phase, this is also gas phase, bulk concentration, and this is the YB star, that is the equilibrium concentration of XAB, and this is called overall driving force on gas phase basis. So here, because you know YAB minus XAB making this driving force, okay, because liquid phase and gas phase, it will be difficult. But for heat transfer it was easy because both was same as a temperature. But here you know that XAB, YAB, there will be some difference. So you have to make this driving force based on the gas phase. Okay, gas phase. How will you do this? YAB is good, So whatever the xp, I will take that corresponding the equilibrium concentration. So now this YAB minus YAB star, this will be that driving force on gas phase basis. Similarly, I can write that Na equal to xi is known. So Na based on the liquid phase, if I write this one. So xab is there, okay, same. Now this I have to convert into in terms of liquid phase. So whatever the YAB is there, so I will go to this equilibrium curve, and that corresponding concentration is my xab star. Okay, so this is the xab star. What is this xab star? It is the equilibrium concentration of YAB. So here YAB I am converting in terms of xab star. So this is the overall driving force, but it is on liquid phase basis. Do you understand? Now if you see, so if I take this is now that the overall driving force on gas phase basis is this YAB, this there, whatever xb I convert into with equilibrium relation xab YAB star. So this is the equilibrium concentration of xab, and in this case this is xab is okay because I want to say there, and whatever the YAB the xab star, it is the equilibrium concentration of YAB star. So in this case the overall driving force is this. So here I am converting the driving force either in gas phase basis or in liquid phase basis with that corresponding equilibrium relation. So if I do this now, so my YAB minus YAB star, this is the overall driving force on gas phase basis. Now Na equal to capital KY, Na equal to capital KY, and driving force is YAB minus YAB star, because what it will be xab, that corresponding equilibrium concentration on gas phase side, and this is called overall gas phase mass transfer coefficient. It is very much similar to your overall heat transfer coefficient, isn't it? So here two phases I am taking. Okay. Now similarly I can calculate the whole thing on basis on liquid phase. So for liquid phase, the overall driving force xab star minus xab, okay, on liquid phase basis. Now that flux equal to capital Kx into xab star minus xab, where capital Kx is the overall liquid phase mass transfer coefficient. So here I am converting in terms of taking consideration of both phases, because if I generally equilibrium curve will be known to me and bulk concentrations will be known to me. Okay, so if I know the bulk concentration in this case, and here bulk concentration is corresponding with this equilibrium curve, I can calculate easily this, and here also similar. Okay. Now thing is this, I told, okay, this is my Kx, this is my Ky, and this is my Kf. These are the overall mass transfer coefficient on gas phase basis and liquid phase basis. Now what are the values of Ky or Kx? That I have to know. Let's see this one. So I can write for the, like in taking that let's take, I'll take the gas phase side. Okay, Na equal to Ky into small ky. So small ky means Yab minus Yai. Similarly, if I take Kx is equal to Xai minus Xab. That is the driving force, isn't it? Xai minus Xab, already we know. And now what we did, capital Ky into Yab minus Yab star. Okay. So Yab minus Yai equal to Yab minus Yn by small ky. Similarly, Xai minus Xab will be Na by small ky, Kx, and Yab minus Yab star equal to Na by capital Ky. So this relation I can write, because flux that will not change. So I express the flux in terms of gas phase side. This is for as a expressed as per liquid phase side, and this is expressed as overall based on gas phase driving force. Now I can write Yab minus Yab star, Yab minus Yab star. This is equal to Yab minus Yab minus Yi plus Yai minus Yab star. I can write this minus this equal to this minus this plus this minus this. I can write this one. So now this part is same. Now here what I am doing here, this part I kept same. Here I am writing Xai minus Xab. So Xai minus Xab. So I divided by this. Then I will multiply the same, because why I am doing, because Xai minus Xab is there. Okay. Now what I can write, so this part is same and this part is same, and now what is Yab minus Yi minus Yab star, this minus this by this minus this. So that is nothing but a slope of this line, this point and this point. If you see, this minus this minus this by this, so this is the slope of Sn. Okay, this is the m dash. Okay, I am writing, and m dash, see here in this case I have taken the generic equilibrium curve, but if it follows the Henry law, that m dash will be m, then it will be straight line. Okay, so then that will be same as a Henry constant. So but here in this case I have taken the generic term, but keep it in mind, when it will be this equilibrium curve will follow the Henry law, then m dash will be m, the Henry's constant. Now if it is the case, now this Yab minus Yab star equal to Yab minus Yabi plus m dash Xai minus Xab. Now what is this Yab minus Y star, capital N by K, Yab minus Yi equal to N by small ky, and Xi minus Xab, this is m dash is Na by K. So Na will cancel out, 1 by capital Ky by 1 by small ky plus m dashed by Kx. So overall heat transfer coefficient based on gas phase driving force, this is the expression. So 1 by Ky m dash by Ky. So now if you understand, see this one, what is Ky equal to mass transfer coefficient based on gas phase. The 1 by Ky, this is the resistance. This is the resistance of the gas phase, and m dash Ky, m dash by Kx, this is the resistance of the liquid phase, and 1 by Ky, this is the overall resistance based on gas phase basis, because capital Ki is the coefficient, mass transfer coefficient. 1 by reciprocal of mass transfer coefficient is your resistance. But this is the relation you can calculate the overall driving force based on gas phase basis. So 1 capital Ky you can calculate. So you need the both the value of Kx, Ky, Kx with this that slope. Generally for load dilution this will be Henry. Similarly, you can calculate this mass transfer coefficient Kx based on the liquid side. How will you do this? So I can write same thing, Na equal to Ky, small Ky equal to YAB minus YI for gas phase, liquid phase Kx into XAI minus XAB, that is same, and then this is overall mass transfer coefficient based on liquid phase, then driving force will be XAB star minus XAB, okay, and this is the Kx is the overall driving force. So now we know this is equal to capital N by Ky, this equal to capital N by small kx, and this will be equal to N by capital K, just like previous thing. Okay, now this one I will again do the similar way. So XAB star minus XAB, XAB star minus XAB, okay. So this I can write XAB star minus XAI, XAB star minus XAI plus XAI minus XAB, okay. Now what I will do, I am multiplying, I dividing by YAB minus YI, YAB minus YI, and then I am multiplying with YAB minus YI. Okay. Now what is this? Now YAB minus YI by XAB star minus XAI. Okay. So if you take this by this, so this is nothing but this is the slope of this line, M double dash. Okay. So but it is a reciprocal, so I can write 1 by M double dash, okay, into YAB minus XAI plus XAI minus XAI. I kept this same. Now I will put this value. So this is equal to N by K, capital Kx, overall mass transfer. This 1 by M dash is there, so this is equal to N by small ky, and this will be N by capital Na by capital Kx. So now Na will be cancel out. So overall mass transfer coefficient based on liquid phase, this is equal to this relation, where M dash is the this slope, or M double dash. For gas phase, this that was the slope was this, and in this case slope is this. But because here different slope is there, M dash and M dash and M double dash, because I have taken the equilibrium curve generic, the slope is changing in. But if it is a in case of Henry law, so then what will be y a will be mx xm. So then this equilibrium curve will be what? Linear. If it is linear, then m dash will be equal to m double dash equal to your m. Okay. But here I have taken the generic term, that's why that I have taken that m dash or m double dash. So now this is the overall mass transfer coefficient. So this is the overall mass transfer coefficient based on liquid phase. Okay, by driving force I am taking as a liquid phase. So 1 by kx is the total resistance, and this is the kx is the mass transfer coefficient for the liquid side. So 1 by kx the resistance from the liquid side, and this is the resistance from the gas phase. So similar thing. So 1 by ky equal to 1 by capital Ky equal to 1 by small ky plus m dash kx. So 1 by ky individual gas phase mass transfer resistance. Okay, this is the resistance is coming from the gas phase, and m dash kx individual liquid phase mass transfer resistance on gas phase basis. Okay, so this is the liquid phase, and this plus this, that will be your total resistance. Okay. Similarly, if you calculate this 1 by capital Kx, that is overall mass transfer coefficient based on liquid phase basis, then 1 by m double dash ky plus 1 by kx. So this is the total. 1 by kx is the total overall mass transfer or total resistance, and this will be the individual liquid phase mass transfer resistance, and this part will be the individual gas phase mass transfer on liquid phase basis. Okay. So you understand, when two phases are in contact, there are two boundary layers. One is from gas phase side, another is from liquid phase side. So the resistance is coming from the both. So when there will be a boundary layer, there will be the resistance, and at the interface we assume the resistance is 0. So two resistance are there. One is gas phase side resistance, one is liquid phase side. So this is the gas phase side and this is the liquid phase side. Now fractional resistance offered by the gas phase side, that is the resistance offered by the gas phase by total resistance of the two phases. So 1 by ky, this is the resistance from the gas phase side, by 1 by capital Ky, that is the total resistance. Okay, so and similarly, if fractional resistance offered by the liquid phase side will be liquid phase side, what is 1 m dash by kx, that is a liquid phase, by total resistance 1 by ky. So this is very important aspect, because you have to first identify for a system which side offering the more resistance, gas phase side or liquid phase side. Now if gas phase side is offering more resistance, then you have to concentrate on this, that I should decrease the resistance of the gas phase side, then automatically flux will increase. Then, but let's take our gas phase side has a much resistance, but if I try to decrease the liquid side resistance, then nothing will come, because controlling part is gas phase side, which side will offer the more resistance. We have to concentrate on that part to nullify this resistance. So first I have to identify in interface mass transfer which side is offering most resistance, so that you can calculate from this. Okay, so if you see okay, gas side is offering 20% resistance and liquid side is offering 80% resistance, so then you need not to worry about gas side. So you try to decrease the resistance of the liquid side. Okay, isn't it? So that identification is important. So I have this one 1 by capital Ky by 1 by small ky plus m dash by kx. This is my equation. This is the total resistance, and this is resistance from the gas phase side, this is resistance from the liquid phase side. Now let's take the case of highly soluble gas. Highly soluble gas means what? Ammonia in water. So if it is highly soluble, at equilibrium the liquid phase concentration will be higher. Let's take liquid phase is 0.6 and gas phase will be lower. Let's take 0.1 gas phase Ya, that equilibrium star, and this is x star. Then what will be M? M will be one by 6 less than 1, isn't it? So for high, and we know that for that one curve will be flat because liquid phase concentration will be lower. Last day we discussed about this. So for highly soluble gas, m dashed, okay, or slope will be small. If it is like this, okay, if this is m dash small, that means this liquid phase resistance will be negligible because this is small, so this by this will be negligible. Then the gas phase side will be the controlling resistance. Okay. You understand this? When some gas is highly soluble, when once it will come to the liquid side interface, immediately it will be taken to the bulk because there is a high affinity to M. So there will be resistance will be very negligible, and then that time the main resistance will come from the gas phase side. Okay. So then in this case, so if I increase the flux, so I have to concentrate on the gas phase side. I have to concentrate on the gas phase side. Why? I have to increase the, let's say I increase the air velocity so that that boundary layer thickness should decrease. Okay, then the mass transfer coefficient of gas phase will increase. Then automatically, because liquid phase has a very negative, I need not to start the liquid phase. Okay, if gas phase resistance, there is a resistance from the gas phase side, so I will make more stirring in gas phase, not in liquid phase. Liquid phase stirring, nothing will happen because there is no resistance. So when for highly soluble gases, okay, m dash will be small, liquid phase resistance will be if it is small, mathematically this will be the negligible. Therefore absorption of highly soluble gas is gas phase resistance control. Example is absorption of ammonia in water, highly soluble in gas phase resistance control. Similarly, if I take low soluble component, that solubility of oxygen in water, we know that here this is 0.21 and here Y star, and what is X star? 8 into 10 to the power minus 5. So you understand, M will be 0.21 by 8 into 10 to the power minus 5. High number, it is greater than, much greater than 1. Okay. So for a low soluble component, the m dash will be large. Okay. If m dash is large, okay, then this resistance will predominate. The fractional liquid phase resistance become the high, and that time, and we say that the rate of mass transfer controlled by the liquid phase. This time this will be negligible small, and this will, let's say total resistance equal to, then gas phase is 10%, liquid phase 90%. Then I have to, in this case, if I start the gas phase side, if I increase the value, nothing will happen. Then this time I have to concentrate on starting at the liquid phase. I have to reduce the boundary layer so that then overall mass transfer, so that flux will increase. So identification in where is the resistance, that is very important. And if you can see, there is a direct relation from the thermodynamics. Okay, what is this slope is there? The slope is nothing that Henry law. Okay, Henry law. Okay. seeing this value you can understand whether it is less soluble or highly soluble. Okay, for less soluble m will be greater than 1, and when it will be more larger, that means it is very less soluble, and m is less than 1, then it is soluble. But if it is very low, that is very highly soluble. That you have to understand this thing. But now you should concentrate on the numbers. Till now you did not, in Henry law, okay, m is there, but now you have to think what is the value, and accordingly physically what is going to happen in your system. For example, the absorption of oxygen in aqueous media in an aerobic fermentation, solubility oxygen is low, is liquid phase resistance control. Okay, so depending on this value of m dash or Henry's constant, accordingly the situation will arise. But if you understand this concept, then you can easily identify which phase is offering resistance. But in general, if it is highly soluble, then gas phase will give the more resistance, and if it is a less soluble, then liquid phase will give the more resistance. But sometimes it happens, absorption of pure gas. Okay, if it is happening, absorption of pure gas, let's say only ammonia is there, I am taking this thing in liquid, pure ammonia. So in pure ammonia there is no non-diffusing part. Okay, so there won't be any gas phase resistance. Whatever the solubility, there is no resistance, gas phase resistance. This is because in such a case the solute does not have diffused through another gas, and its partial pressure at the interface is same as in the bulk, so gas phase will not offer any resistance. So in case of pure gas, so gas phase will not give any resistance, then that will be the resistance from the liquid side. Okay. Now we have considered that here m dash m, okay, so absorption, because from this point to this point. Now if you let's take, I have a point, XAB is this and YAB is this. That means liquid phase concentration is high and gas phase concentration is low. Okay, now we will take the same slope, minus kxy, I will this here. So in this case, so if you take this one, this case, XAB and corresponding, this will be your YAB, so that means what? When this point is below the equilibrium curve, then mass transfer will take place from liquid phase to gas phase, because this is the driving force I have. Okay, and this will be your YAI, this will be your XAI. So in this case I have considered when this is the gas phase concentration was high and liquid phase concentration, so then there is absorption. Okay, so mass transfer is happening from gas phase to liquid phase. But when it is like this, then that if you see that in this case driving force is YAI minus YAB, means minus of YAB minus YAB. Okay, in this case mass transfer will take place from liquid phase or to gas phase, that is called stripping. Okay, so stripping means what? In liquid phase the concentration is high, gas phase is low. Same thing, if you see this M point, this is the M dash point, and in this case mass transfer is happening from gas phase to liquid phase. So gas phase concentration is high, liquid phase concentration is low. Okay. So then this is the slope here, and in this case, and this is the driving force in this case. But when it will be this is the XAB, and this is will be low, and what will be the driving force? This minus this, so negative of this. Okay, but if you make the calculation, everything will remain. But in this case, mass transfer will take place from liquid phase to gas phase, and that is called the stripping. That's why if you see, absorption and stripping is taught in a single chapter. Conceptually same, but you have to see the point. The equilibrium curve is there, your M point is above this equilibrium, then G phase to L phase. And if M point is below this equilibrium curve, then it will happen, mass transfer will happen from L phase to G phase. So this is, so the point M, which indicates the bulk concentration of the phases, is located above the equilibrium curve for a particular choice of the coordinate. So there is a opposite driving force. So if you see that M dash from gas phase to liquid phase, if bulk concentration represent by M point, means this point, which is below equilibrium curve, the driving force will be YB minus Y turn becomes negative. So there will be a transfer of solute from from liquid phase to gas phase. That is the desorption or stripping. And whatever the above discussion and derivations we have taken in the example of mass transfer in gas liquid system. So although we have discussed this thing for the gas liquid system, but if you consider any two phases, same theories will be applicable. That a similar treatment is valid for any other system, for example liquid system, or gas solid system, or liquid solid system. Whatever system if you take any, although we have taken here the example of gas or liquid to understand the concept better, but if you take any two phases, G phase, if you take the, instead of gas phase liquid phase, if I take the G phase and L phase, and G phase L phase can be any two phases, either liquid or gas solid or liquid solid, any two phases it will be accurate. In a real mass transfer equipments, the intensity of the turbulence or mixing may vary from one point to another. If it is varying, as a result, the individual and overall mass transfer coefficient may not remain uniform throughout this equipment. I told this thing, so then an average coefficient is normally used in such cases. So if I take this, let's take driving force in gas phase is partial pressure, okay, corresponding that kg will be mass transfer. Driving force of liquid phase, it is this one. Then this, similarly, that if you take the overall mass transfer from gas phase, liquid phase, then it will be with the end this condition. If you make the similar concept, it will come. Okay, thank you for your attention. Bye.